She is an assistant professor with a joint appointment in both the Department of Biomedical, Biological, and Chemical Engineering in the College of Engineering, and the Food Science program here in the College of Agriculture, Food, and Natural Resources here at the University of Missouri. She uses sustainable food processes engineering tools for value-added processing of fruits, vegetables, ancient grains, underutilized agroforestry crops, specialty crops, and medicinal plants. She looks at post-harvest processing to prevent food loss and waste, and she's very much focused on developing innovative technologies to deliver and fortify foods with micronutrients. She likes or thinks of her research as aligning with the Sustainable Development Goals, Sustainable Development Goal number 2, to reduce malnutrition and improve food security and nutritional security. She is a collaborator with the Center for Agroforestry, and increasingly we've been looking at new collaborations around specialty crops, elderberry, pawpaw, black walnut. So we're very pleased to have Kiruba here as a new faculty member. So thank you very much.
Thank you, Gregory. Thank you. Yeah. Good afternoon, everyone. I'm Kiruba, and today we're going to talk about food processing innovations. So how did I become a food engineer? It's because I really like chocolates, and I wanted to know how do they really make chocolates. So when I finished my high school, I was looking into universities that was teaching this skill. And it was only one university in India that was offering that course. It's called Tamil Nadu Agriculture University. It's one of the oldest land grant institutions in India. And Cornell University had a dual degree program with TNAU. And then McGill University had an international, multi-million-dollar international collaboration on consolidation of food security in South India. And so what did they do? They set up a pilot plant for processing of food. And this is an example of a plant where we have different unit operations put together. And generally, when we have small-scale farmers or horticultural farmers and specialists who want to process food, they always come and say, oh, we don't have a specific equipment for the product or the raw material that we're looking for. So what this pilot plant we were doing, we were modifying existing technology, because there's no point in reinventing the wheel. If there is a technology, we could adapt it to the needs of the end user. So here, this is a processing unit where we have sugar syrup, and you can have your pasteurization unit, the kill step, and mix different flavors, everything controlled through the pipelines. And then it goes into a filling unit, and then we can have different products from the same unit. So likewise, here I wanted to show this was a mango processing system where you could blanch it. Then there's a pulping system here. A similar thing that could be used for the pawpaw here, because if we could change the parameters, the mesh size, we could use a similar system. And then a chili processing unit where we had people from the extension who will teach the farmers about growing high-quality crops and then drying it. And then afterwards, we could this is a ribbon blender. It's used for blending different spice mixes. So then it could be packed and sold in the market. And this is one of my favorite projects. That is, we were improving the livelihood of rural women. Because in most of the countries, you have a lean season and a surplus season. During surplus season, we have tons of tomatoes produced, and we don't have enough capacity to process it. So what farmers do is they generally dump it down the fields, and it's a lot of waste. So what we did is, during summer, we bring women from rural communities and teach them how to process small-scale tomato processing, so they could use that value-added material and increase their livelihood. And the biggest story is, whenever every year, the women, they come, they get trained in one technique, another technique, a retort pouching, or something like that. And every time they come and they say, I used that money to send my kid to school, or I bought some books. So that was the first time I felt like, oh, we could use technology and food processing techniques to improve the life of people. And so then that led to my master's at McGill, and then I did my PhD at McGill. And it's an AAU institution. And then that led to my postdoc in chemical engineering, focused on food engineering. So these are the only two universities outside of US which has AAU membership. And then I'm here at Mizzou. So Mizzou is great because it is an AAU member as well as a land-grant institution. That is such a very powerful thing because you have amazing research and extension that can be translated to the people. So I moved here in 2018, and I'm still learning about Missouri, and I look forward to learning more. So, and there is another important thing about Missouri is that this University of Missouri, Columbia campus is the only university that could offer a course in food process engineering. Because in order to offer a course, one, as an engineer, you have to be accredited by ABET, which is the accrediting organization. And we have to be accredited by IFT, that's Institute for Food Technologists. And since the Food Science Department, we are the only school in the state of Missouri that's accredited by both. So we could offer this course, and I'm teaching that course. And these are some of our peer institutions that has the same capabilities. And as I said, I'm still learning about Missouri. But one thing that attracted me is there's so many industries, food industries in Missouri, and there are so many opportunities that could be developed in the state. And so that's the overview of me coming to Mizzou. And here, what is food process engineering? When we ask this question, people say, like, I would define it like this: science applies scientific methods to understand the natural world. And engineering applies those scientific principles to develop process or products. And technology is developing those processes and products to meet the needs of the society, meet the wants of the society. And I would say food engineering is somewhere in between here because it connects all these things. So that leads to another question: what is food science? So food science is it's an interdisciplinary STEM field that connects engineering, chemistry, microbiology, law, nutrition, horticulture, biochemistry, and so on. And that engineering here, that's where we do the food process engineering. And when we talk about food process engineering, what do we really do? We take raw materials and we transform them into safe and nutritious food. Safety and nutrition is like food safety, nutrition, and engineering. These are kind of the three pillars of food science. So this is what we do in food process engineering. But this topic is about innovations, right? Food processing innovations. So what do we mean by innovation? So how many of you recognize this person? Okay, thank you. For those who haven't raised your hand, did you have the Beyond Meat burger in the lunch? How was it? It's good? So this is the person who invented it, okay? Yes, he's an amazing food engineer. Above all, he's a great human being and a great mentor. So that's Dr. Fu Hongxue, and he's now a professor emeritus at University of Missouri. So I've kind of inherited his lab. So that equipment you see behind, that's an extruder that was used to make the first prototype of Beyond Meat. So let's talk a little bit of innovation here. Taking raw materials and converting into food product, that's common. When we think of innovation is you take materials and you envision a product that is not existing and you develop it. So here, what Dr. Shea did, he took soy protein isolates and pea protein, and then he used an extruder. So this is an equipment that was used to make the mock meat. So you put the material inside this, and you have different zones, and each and every different zone, you can increase the temperature, the pressure, the flow rate to give and mimic the texture of meat. So that's what was done, and by optimizing this technology, you could get something that is now in the market. And this is what we think of it, taking something, imagining a product, and making it into a real-time product. And so this, in a small scale, we can do. But the biggest challenge that I hear or I see is scaling above such technologies. When you're thinking of scaling up, then you need to think of much more. you need to think about the HACCP, the critical control points, the kill steps, and so many aspects that goes into making a product from your kitchen or your lab to a pilot scale up, then to a large scale up. So there are different steps involved in scaling up of a simple technology. And you see here you have a lot of like control units, like drums, and then you have a conditioning unit, and this is an extruder. Pretty much this is an extruder, and the material goes into a drying chamber, cooling chamber, packaging chamber, labeling. There are so many things involved in making that one product that you had today in like during lunch. So to sum this up, you could take a technology that was developed in a lab, like at Mizzou lab, and it could reach global market. So this was a picture taken in Tim Hortons. So I was in Canada, and we were standing in a line with my friends, and I saw this Beyond Meat sausages. So I told my friends, that particular product was made in Columbia, Missouri. And I was having it in Toronto, Canada. So that's the possibilities that could happen if taking an innovation and scaling up. And we know what is happening with Beyond Meat. It's expanding, and they're going to build another plant and recruit 600 more people into that plant. So something that started in a lab can have that impact. And the example is it happened here at Mizzou. So that's one success story. And what I'm interested, as Gregory mentioned, I'm interested in sustainable food engineering. So why sustainable food engineering? It's because in the year 2050, we had 2.5 billion people. And now we are around 7.5 billion people. And by the year 2050, it's predicted that we're going to have 9 billion people on this planet. So the big question is, how are we going to feed these people with healthy foods? We could feed them, but we want to feed them with healthy foods. So that's a big question. And food system is a very complex system. It is interconnected, and you have to, in order to make that impact, we have to think of partnerships. How can we partner with others to make that happen? And that's what I'm trying to address in my research. That's a nice. So the big question that I'm asking here is, one side, we have around 821 million people affected by chronic hunger. How many of you have heard about hidden hunger? Yes. So hidden hunger affects 2 billion people. That is hunger due to micronutrient deficiencies like vitamins and minerals. And people think that it happens only in the developing countries. No, it happens everywhere. Every country on this planet Earth is affected by hidden hunger. Because one side of this hidden hunger, you have undernourishment and stunting. On the other hand, we have obesity and overweight. So both of these things fall under the same umbrella of malnutrition. And we know, so every country on this planet is affected by hidden hunger problem. So that's one problem. On the other hand, you have 1.3 billion tons of food getting wasted. When I'm talking about food waste, it's not it encompasses both the food that's dumped down in the, in the cafeteria, as well as post-harvest losses. In the field, we have so much of food, post-harvest losses happening. 40% of produce that is produced is not reaching the people. So how can we address this? So these are the two challenges, and my research team is called the FEAST research team. What we are trying to do is, if we could find innovative food processing techniques, then we will not be calling this as waste, but it will become raw materials for your processing. A waste is a terminology that was developed by humans. In nature, there is nothing called waste. Everything had its purpose. So if we could develop new technologies and new process, then that becomes a raw material, and we will be able to address certain problems. Not all the problems, at least a little bit of these grand challenges. So how we address it, there are different ways of approaching this big problem. I'm taking a smaller, these three approaches to address this big challenge. One is sustainable food engineering. That's where value addition to food loss, food waste, post-harvest processing of fruits and vegetables come into place. And then once we develop that, fortifying those nutrients, that food with micronutrients to prevent hidden hunger problems, and then delivering it. Because most of these micronutrients are heat liable, so you need to deliver it in a proper encapsulated form. So that's the encapsulation part of it. And all those things aligns with the Sustainable Development Goal 2. How many of you have heard about SDGs? Great, thank you. So SDGs, in the year 2015, around 193 countries joined together to develop a plan, an agenda for both our people and our planet. In the year 2030, if we are able to address most of these challenges, we can have a sustainable system. So my research aligns with that goal number 2, zero hunger. So let's come to the specialty crops in Missouri. So I'm still learning about Missouri, but I had this great opportunity to visit some of the processing units, like the Black Walnut facility. It was a wonderful facility. Thank you. And then we had some pecan facilities and visited some farms. And I was really surprised because as a process engineer, when I see commodities like raw materials, it just excites me because of all the products that could be developed through those materials. So here is one technology I'll be talking about. It's called a spray drying. So using this equipment, what we could do is we could convert any liquid into powder, or we could do encapsulation. So we could encapsulate flavors, color. So many things could be encapsulated, because if it's in a liquid system, the shelf life of a product might be deteriorated over time. But once it's in the powder form, and then it could be reconstituted. So this is one technology. And this is, we got some blackberry samples from the Agroforestry Center. And what happens is, you have your formulation, and that formulation gets into a peristaltic pump, and it goes into a atomizing nozzle. Here, it sprays in 150 microns, very fine droplets. And there's a convective heat transfer happening here. Then it gets into a cyclone separator, and then you can collect your powder here. And so let's see if I can see this. So you could see the material going into the pump. So you have three-way nozzle. By changing those nozzles, we could encapsulate or make into powder. And you can see there, the liquid gets sprayed into the chamber. And then you can see the powder getting collected in the cyclone. So this whole thing, in an industrial scale, it will be like in an industrial scale, this whole unit will be like an 8-story building. But in a lab, it's just like a small little system. Because if you want to optimize a formulation, it will be easier to do it in a lab scale and then scale it up to an industrial scale. If you're going to do the other way around, there's a lot of raw material loss, and the time-temperature combinations might vary. So generally, in food processing, we try to optimize things on a smaller scale and scale it up in sequential order to meet the needs. And currently, what we are doing is we are working with black walnuts and blackberries, and like soybeans, grape pomace. And I look forward, I heard so many materials like pawpaw and so many horticultural commodities. I would like to get some samples and see if we could develop new innovative products with those materials. And I'm also interested in medicinal plants. So, okay, right. So, to sum this up, how many of you read that the Show Me State Food, Beverage, and Forest Product Manufacturing Initiative? Great. So it's really a wonderful booklet that gives you an overview of all the value-added processing capacities that could be used in the state of Missouri to improve its economic development. And this is my understanding. This is a small summary of that. So we have agricultural, Missouri agriculture, forestry, and the production system in place. And 2 ways of getting those raw material. One is the feedstock industry, where processing takes place. We use the same equipments. Whatever is used in this thing could be used in the food industry as well. Then it goes into distribution, and that gives economic security. And the same materials, the food materials processed, distributed, could lead to food and nutrition security. And from the report, it says there is an opportunity to lead like $71 billion of economic activity, around 70,000 new jobs, and around $4.4 billion of new personal income, and overall happy and healthy Missouri. So it is possible. And you might think, where is your market, right? You're developing all these things, where's your market? The food industry is a very big global market. They're always looking for new products, new ingredients, and new supplies. So there is a market. Are you ready to give those innovative products to them? And since this topic is mostly about food processing innovation, I would like to leave you with this particular thing. If you could imagine a product or a process, it's possible. We could find a way to make it happen. And another thing is, I was listening to Dr. Jim Spain, and he said something that really, really inspired me. I want to share that with you. We did not invent the light bulb by improving the candle. Thank you.
Thank you, Kiruba. That's a very inspiring presentation. Let's see, we have some time for questions, please. I think right here.
Before you get to the point where you're scaling up and you're trying to match the product in the market, are there ways you can test things out, particularly for small producers, to, I guess, perfect the market before you go to scale?
Yeah, thank you. That's a great question. So before we scale up, generally we have to do in steps. If you're doing in a small scale, 10 pounds, then you do 100 pounds, then you do 1,000 pounds, then 10,000 pounds. That's how you do in scaling up. Because whenever we are increasing the capacity, every unit operation, you might be thinking just a mixing step, right? Small scale, it's possible. But when you have 10,000 tons of material, that simple unit operation of mixing becomes a big challenge, because you'll have a space separation on the top, then the down material will not be mixed properly. So these are all the scaling factors we say. That's why we do these small scale pilots and then go to the large scale. And as a process engineer, when we develop those flow diagrams, we do a material balance for every step. And that information will be passed on to the scaling engineer, who could use that information to plan the design accordingly.
I guess the follow-up question is, how would a small producer hook up with those pilot programs that then, before it goes to scale, to perfect the product?
Okay, thank you. So now we are trying to hire more people into the food engineering area. So a process authority, state process authority. And then once we optimize the formulation and the process, there are food industries. There's a big, IFT is a big network where you can connect with industries, pilot scale operations, where you could do a small scale trial in another industry where they have all those equipments and try if your formulation is giving the same results. And once you get into that network, we'll be able to help you out with that. And we are getting a state process authority and another food engineer. So we are trying to build the food processing and value-added processing infrastructure in the state as well as in the University of Missouri.
I'm interested in the nutrient content of the food after it's processed. Yeah. Do you know if there's any loss of nutrients after it's processed?
Yes, thank you. That's a good question. So whenever we develop a formulation or process, we have to understand and study the nutrient content, the safety of both the raw materials as well as your product. And then you optimize based on which formulation or which time temperature combination is giving you the highest micronutrient or the nutrient profile with least anti-nutrient and having a longer shelf life. So we do a shelf life study and optimize these parameters, and those best combinations go for the next pilot study.
Okay, well, thank you, Kiruba.